Here's another tension problem, but it's a different kind of tension problem because we've got two objects involved here. Let's imagine we've got two masses, M1 and M2. There is a rope attached between them and another rope going off to the right from M2. So this rope is being pulled here, and it's then going to pull M1 and M2 along on the surface. And just for the sake of simplicity for this problem, we'll assume that it's frictionless. The surface between M1 and the floor and M2 and the floor is frictionless. We could certainly add in friction here if we wanted. That would just give us one more force acting on each of the two masses. So how are we going to solve this? Well, we know we're going to have some tension over here. Let's imagine that it has some given value. So let's imagine we know that this is some tension T2. But let's imagine that the tension between the masses we don't know. So let's imagine that this rope has got some tension T1. So let's imagine we know the masses, and let's imagine we know T2. Let's see if we can figure out, given T2, what's T1, what is T1, and then what are the acceleration of the masses. Let's see if we can actually figure that out. All right, very good. Well, one thing we do know is that whatever the acceleration of M1 is, it's going to be the same as the acceleration M2. We're going to assume that the string or the rope does not stretch at all. It's not a spring, so however M1 moves, M2 is going to have to move the same amount if the rope is not going to stretch. So whatever the acceleration is of M2, it's going to be the same as the acceleration of M1. Okay, now how is this tension T1 going to act on the two masses? Well, tension T1 is going to be pulling back to the left on M2, while T1 is going to be pulling to the right on M1. So the tension T1 is actually acting in opposite directions on the two masses. All right, so let's look at what does Newton's second law tell us. We're going to use F equals ma. Remember, the net force equals the mass times acceleration, but we're going to apply it separately to each object. Let's apply it first to M1. We know other forces that are acting on M1 will be the weight and the normal force, and those will be the only forces acting in the vertical direction, so we know those will cancel out. Likewise, M2 will have its weight, we'll call this W1 and W2, and then it will have its normal force, Fn2, call this Fn1. And those will balance each other in the vertical direction. So all we really are worried about in this problem is motion and forces, or all we are worried about are motion and forces in the horizontal, or let's say the x direction. All right, let's apply F equals ma for M1. What force or forces are going to be acting on M1, and in this case in the x direction? Just T1. So we know that F1, the net force on mass 1, is just going to be T1. And that must equal then M1a. Then what about M2? Well, we know the net force on M2, F2, is going to be, well, T2 in the positive direction, and then T1 in the negative direction, so minus T1. And that's got to equal M2 times A. All right, very, very good. Again, we've got two unknowns. Let's not worry about these F's there. We've got two unknowns. We don't know A and we don't know T1. So let's solve for one of those first. Well, we've got T1 here. Let's take this and put this in for T1 over here, and then we'll only have one equation with one unknown. So what do we get in that case? Well, we get T2 minus T1, which we'll write as minus M1A, equals M2A. There we go. Let's bring this over here, and we get T2 equals M1A plus M2A. In other words, M1 plus M2 times A. Let's divide by the sum of the masses, and we have A equals T2 over M1 plus M2. There's our solution for the acceleration. Now let's think about that in relation to that other problem that we looked at before with internal forces, so to speak. If we could imagine just M1 and M2 as basically being attached together, not just by a rope, but imagine that they're a single object. On a frictionless surface, the only force acting on this single object is T2. What would we expect its acceleration to be? We would expect T2 to equal the total mass, M1 plus M2, times its acceleration. In other words, A would be T2 over the sum, M1 plus M2. So this is what we might have guessed right from the start if we had just thought about this as being a single object with a mass of M1 plus M2. However, we can now take this and come back up here, T1, yep, come back up here and figure out what T1 is. So we can take this and put it in here, and what do we find? We find that T1 is equal to M1 times the acceleration, which we found to be T2 over M1 plus M2. In other words, T1 equals this ratio, M1 plus M2 times T2. There we go. That is a very, very interesting result. Let's look at this for just a second. What kind of extreme values might we get for this? Let's look at this with some extreme relation between the masses. Let's imagine that M1 is much, much, much less than M2. So M2 is maybe 1,000,000 times bigger than M1. So maybe M1 is like 10 kilograms and M2 is 10 kilograms and M1 is 1 microgram, something like that. All right? What do we get in that case? Well, M1 plus M2, that is basically just going to be 1 microgram plus 10 kilograms. It's basically just going to be M2. Let me write this out. For M1, much less than M2. This symbol is two less than symbols, which means it's much, much less than M2. So it's not just less than, it's much less than M2. What does that mean in that case? Well, M1 plus M2 will basically be M2. You're adding a tiny, tiny bit to a big number. That's going to be negligible compared to that. So we get basically M2. M1 over M2 is then going to be a very, very tiny number. So what we end up with is T1 is negligible compared to T2. Well, that makes sense. We come over here, if we're pulling on M2 with a force of T2 and T1 is much, much less because it's only pulling T1, then we could basically ignore T1 relative to T2, and if we come down here, ignore M1 relative to M2, the acceleration of M2 is just basically going to be T2 over M2, and that's what we would get if we just completely ignored the presence of M1. Well, that makes sense, okay? The force over here is negligible compared to T2, and we can basically ignore it when determining the motion of M2. What if they're, let's say, equal to each other? What if we have equal masses? M1 and M2 are equal to each other. Well, then, so if they're equal, what happens in that case? Well, look over here. We have that M1 plus M2 is basically the same as 2 times M2, and we have the acceleration is T2 divided by 2 times the total mass. Yeah, well, that makes sense. But what about over here? We have that M1 plus M2 is like 2 times M1, say. M1 over 2M1 is 1/2. T1 is 1/2 of T2. So 1/2 of the tension, 1/2 of the tension to accelerate 1/2 of the total mass. That makes sense. But then we've got twice the force this way, half the force this way, or I should say, 1 force this way, 2 times that force this way. That cancels one of them, and we end up with the same acceleration for M2. Okay, well that makes sense. That makes a lot of sense. And then what if we looked at, let's just say, for M1 much larger than m2. What do we get in that case? m1 much larger than m2. Again, ignore m2 relative to m1, and we just get the acceleration as t2 over m1. That makes sense. Here, m1 plus m2, if we ignore m2 relative to m1, we get m1 over m1, which gives us 1, which means t1 is basically the same as t2. So that the force, practically all of the force, is still accelerating m1, where you have a very, very small residual force with t2 this way and t1 that way. You'll have only a tiny force needed to accelerate m2 if m2 is very, very small. Okay, well that's kind of an interesting result. We get these results, and it's sometimes very, very useful to look at your results in extreme situations to see why these things make sense. All right, great. Let's take a look at another one.